Hello, good morning. How is everyone doing today? In last week's class, we talked about the equations of motion for a simple harmonic oscillator. What would be considered a simple harmonic oscillator is if you attach an object to a spring. In this case, we're looking at a horizontal spring and the object is attached to the end. We give it an initial condition so that we stretch the spring a little bit and then we let go, right? So if we have a very smooth surface, so friction can be ignored, that you will have the mass going back and forth like that. So that's a simple harmonic oscillator. We solved the equations of motion by setting up Newton's second law. We know that the force is proportional to displacement using Hooke's law, and we know that acceleration can be written using the second derivative of the position with respect to time. So we got a differential equation, we found a solution, and we figure out the constants by using the initial conditions we have. So here we had let the spring go at the maximum stretch. So we say at t equals 0, your position should be at that maximum value. By doing that, we found, okay, so this is our equation that describe the position of the object at any given time. So it look like this is a cosine function, right? So by taking the derivative, you can get the velocity and acceleration for the object. So velocity is also a sinusoidal function. It's a sine function, and acceleration is a cosine function, right? Makes sense for velocity and position to be completely sort of 180 degrees out of phase, because whenever you have maximum position, it's when the object being stretched to a point where it cannot be stretched anymore. So at that point, your velocity is 0. So whenever position is the biggest, the velocity is 0. Whenever velocity is the biggest, that's where you're in the middle, then the position is 0, meaning the stretch, the spring is not being stretched at that point. So we can plot velocity graph, we can plot acceleration graph, and you can see that v is dx dt, which is negative omega d sine omega t. So the maximum value velocity can have, right, is this quantity, because the maximum value sine can have is 1. So that's the maximum value is omega d, and that tells you the amplitude of this sinusoidal function. So this is the amplitude. The same thing goes for acceleration. Acceleration is the velocity dt, which is negative omega squared d times the cosine function. And this is again the amplitude for the acceleration. Okay. All right. So there is also another, excuse me, relationship we can find, that the simple harmonic oscillation describe the position of the object at any given time. It just so happens that if we're looking at a circular motion, the x position of the object is also exactly the cosine function. So let's draw a little bit of graph here. Take a look. So we're looking at a circular motion right here. Let's say the object initially is at an angle phi above the x-axis, okay? And it is moving with an angular velocity omega, okay? So after t had passed by, the angle that it made is omega t, right? So this little angle is omega t, because omega is angular velocity. So omega times t tell you the angular displacement, right? So you will say in 5 seconds, it sweep by 40 degrees, for example. So you can see that the x position of this object right here, the x as a function of time, is the radius r times, in this triangle, times cosine of the angle. So this angle would be omega t plus the initial angle the object had, omega t plus phi. You can see this is exactly the same format as our simple harmonic oscillation. Okay, so if we start with t equals 0, theta is equal to phi. This is our initial condition. And then we have this equation to describe the x position or x coordinate of the object, of the little dot that is doing a circular motion. Okay, so the one that we derived for the spring was x is equal to d cosine omega t. Okay, so this is the amplitude, right? This, in this case, it's the radius. Here we have phi is 0, because phi simply just tell you where the spring is started. If we had our little object starting right here, right? And you can see then the equations for the x position was just be cosine omega t, and there's no phi. Phi simply tell you like where are you starting. We could have done this with our simple harmonic oscillation. So instead of calling t equals 0 is at the maximum position, we can call t equals 0 when it's in between the maximum and the equilibrium point. So somewhere in the middle, you can give it the a phase. So we call phi simply the phase, initial phase, and this phi tell us the initial location of the object. Okay. So if phi is 0, then you can see that, okay, if it's a cosine function and phi is 0, which means at t equals 0, x is at a maximum value. Well, that tells you initially the object start out at a maximum stretch. You let it go at a maximum stretch. Okay. If your phi is pi over 2, okay, so x is d at t equals 0, then that means x is equal to, so cosine pi over 2 plus an angle becomes cosine, right? Becomes sine. So you can see at t equals 0, x is equal to 0. So you can see that simply tell you at t equals 0, my mass, my object is at the middle point, is at a point where the spring is neither stretched or compressed. That's simply where you call t equals 0, where you start your timer. Like, okay, right now I'm starting to observe the oscillation and I start where the mass was in the middle. T could be some, phi could be some random number. And that just tell you, well, if it's pi over 3, it means that it's in between the maximum stretch and the equilibrium point where you call t equals 0 and let go, right? So, and start counting. So this is really just the phase. So be a little bit careful how they give you the initial condition. If I give you, say, this is a times sine omega t plus phi over 2 plus pi over 2. So if I give you something like this, you can see, oh, there's a pi over 2 phase. Doesn't really mean this because I now have a sine theta, right? So this means at t is equal to 0, x is a sine pi over 2, because this becomes 0, and that is 1. So this is a. So this gives you the same initial condition as this one, okay? Because sine and cosine is really just a pi over 2 phase difference, okay? So they give you, if they give you a non-zero phase, you also need to look at whether it's a sine cosine to figure out where is your initial condition and where is your initial location of your object, okay? So let's take a look at these two different graphs. We know how to draw cosine function, right? That we all know how to draw. The cosine function will simply be at t equals 0, you have a peak. At t equals 0, you should have your peak value here, and then you can draw the rest, okay? And the amplitude would be a. So a tells you what is where is the peak value. So from here to here, that is a. From here to here, so this is a. This is negative a. So draw a cosine omega t. We know how to do it. The period is given by 2 pi over omega. So we know that omega is simply telling us something about the entire time it takes for one oscillation. But if we, how do we draw a cosine omega t plus phi? Okay, so if there is an initial phase, how do we draw it? Okay, so you might wonder, well, I can always, if I know what phi is, I can always plug in different values for t. For example, I plug in t is equal to 0, and x is t equals 0, and my y would be a cosine phi, and then I will plot. Of course, we can do that. But there is a more of a simpler method is to look at, okay, well, this graph is really just the original graph that has been shifted by a phase. It's been shifted a little bit either to the left or to the right. So which way does it shift? We can think about this. Here is at t is equal to 0, this function peaks. But if you have an initial phase, and assuming that phase is a positive phase, then you say, okay, when does this one peaks? It peaks at when cosine is equal to 1, so which means omega t plus phi is 0. So it peaks at t is equal to negative phi over omega. Okay. So it peaks at a time that is earlier than the previous graph. So it peaks earlier. So it peaks at the earlier time. So you simply just draw it a little bit shifted to the left, showing that the peak happened earlier. So the dashed blue line represent this graph, the red solid line represent the first graph. Okay, so if we were given different functions and asked to draw it, we know how to draw it. So there was yeah.
Sorry, could you really quick go back up to the I think it's like 2 slides ago that you have the colored blocks on the text? Yeah, that one.
Okay.
Yeah. Thank you. I just didn't know if I had missed a definition. Okay, thank you.
Okay. All right. All right. So now why do we want to talk about how to draw it? There is a bridge question looking at the combination of two sinusoidal waves or sinusoidal curves added together. Now, the superposition of sinusoidal functions would be very, very useful later on. If you are, for example, in engineering, they do a lot of, in terms of electronics, in terms of our signals, we have a Fourier transformation, and there is always going to be a superposition of sine pseudo functions, sine pseudo signals together. So this is actually quite practical and useful. So what if we just deal with addition of two sine pseudo functions? You don't even have to add more. Let's just add two. So we have this blue one and this red one. Okay. So if we put them together, what do you think the overall curve will look like? What do you think the overall signal will look like? Might be choice A or B or C, right? So there are different reasons you may choose different choices. For example, if you choose choice A, you might think, well, you're just superposition these two together, so how could it be purely smooth? So maybe there should be a dip somewhere. So I'm going to choose A. B says, well, the sum of the two waves with equal frequency gives another signal with the same frequency. But the amplitude and the phase might change. So I choose B. C would, if you choose C, might argue when you add two together, it gets faster. Okay, so I'm going to show instead of oscillating like this, it's more like much faster, more a bigger frequency. So C shows a bigger frequency. It means that in the equal amount of time, it repeats the patterns more often. So that's why you can see these waves are squished more together, showing a bigger frequency. So omega is our angular frequency, or a lot of times you write 2 pi f. If you still remember what f is, f as in frequency is defined to be 1 over t. Okay, it shows, t shows how much time it takes to complete one oscillation, one cycle. Then f means it's 1 over t. It means that in 1 second, how many oscillations you have completed. So if it is 100, then f would be 100. Okay, so when t is seconds, 1 over second, we give f a unit, that's the hertz, how many hertz. So when we say frequency, you can either refer to omega or you can refer to f. It's not really all that different because they are only related by a constant of 2 pi. Okay. All right, so each of all of these kind of makes sense, right? These different reasoning. So now we have the tool of the actual math of these two different functions we're trying to add together. We can simply just try to work it out. So let's take a look at these two graphs. One of them is a little bit ahead of the other, right? So we can simply call one of them to have a function that looks like a cosine omega t. And the one that's a little lagged behind, we can call that is a cosine omega t plus phi. The difference between two of the signals we're trying to add together is a phase shift, is only a phase shift. Because they have the same amplitude, how do I know? You can see that from the peak to the valley, it's the same height. So they have the same amplitude. I also know they have the same frequency. And how do I know that? Because this one from the peak to another peak, that is one entire oscillation, is the same width as from here to here, entire oscillation for the blue one, right? So they have the same frequency. The only difference is one is a little bit behind the other. We call it lagging. If one is ahead of another, we call it leading. So in this case, the red is leading the blue, or you can say the blue is lagging the red. Okay, I know how to describe a function that's a little bit behind. I need to add a phase, initial phase. So I have switched, I changed this question into a math question, algebra question. Now you really just tell me, okay, well, you're adding these two together. So what is a cosine omega t plus a cosine omega t plus phi? If you know what the addition looks like, then you've solved the problem, right? Right, okay, so let's try to add them together. Here we would use a math identity of a trig identity that looks like this. Okay, so what kind of trig identity we need? We are adding a cosine function onto another cosine function. So we look it up with the reference or look up our math knowledge. We see, okay, this trig identity is telling me this cosine A plus cosine B is 2 cosine A plus B over 2 times cosine A minus B over 2. Now I can use this identity. I'm trying to solve is cosine omega t plus A cosine omega t plus phi. Now A is the same. This is A times cosine omega t plus cosine omega t plus phi. So to use this identity, I'm going to treat this as my A, right? And I'm going to treat this as my B. So simply plug in into the identity, you can get the result. So when you add these two together, they become 2 cosine. Okay, the arguments added together, that's 2 omega t plus phi over 2. That's omega t plus phi over 2. And omega t minus omega t plus phi over 2. And that gives you negative phi over 2. Okay, so you can see that the cosine negative phi over 2 is really just a constant because phi is a fixed phase. Whether how much is it lagging behind, let's say 30 degrees lagging behind. So phi is 30 degrees. Cosine of that is simply a constant. This is just a value, some constant. What this function, what this mu function is, it's a cosine function. It's cosine omega t plus phi over 2. So we know exactly how to plot this, right? This is just a cosine function with the amplitude changed a little bit because now you can see you have a different constant multiplied by a. So the overall, let me write the final equation for this. A cosine omega t superposition with another function becomes 2 cosine phi over 2 times a cosine omega t plus phi over 2. So this could be your new amplitude. So a prime, and you just need to plot this function. Okay, so now if this is positive, right, if depending on what phi is, usually the initial phase we give it is some angle between 0 and 90 degrees. So this is certainly a positive value. Then your a is still a prime still positive. So I simply just adjust my a bigger or lower depending on where my a was. Then this is a cosine function, right? So you just need to shift your function to the left because now it has an added phase. So instead of peaking here, you need to peak here. And this top bottom value, this is your a prime. So this is your new function. And let's take a look at our graphs. You can see B is the correct answer. This new function has same frequency omega. Okay, so when you add two waves together, these two have same frequency, they all have omega. You get a new wave, you have a new signal that's also a sine pseudo function and has the same frequency, same omega. So the width of this should not be changed. Okay, all right. Okay, so that is one of the bridge questions we looked at. You can see the key for answering this question is knowing how to identify the mathematical expression for a function that is a little bit behind or a little bit ahead, and then use a trig identity to find the new one. All right, now let's look at some more questions, and these will be, you will answer these. So the first one we're looking at, okay, we have a mass that's oscillating on the spring, and they tell us the position as a function of time is a sine pseudo function shown here. We're trying to figure out the signs of the velocities and the signs of the acceleration. can we tell from the graph which point have positive velocity and at that point the acceleration is negative? Okay, so you know positive is simply, well, it's in the positive. So according to my definition, right? For example, at point A, I have a positive position. So here, this is a position time graph. So can you tell from the position time graph which one has positive velocity and which one has positive acceleration? All right, so I'll let you have a minutes or two in the breakout rooms to discuss this, and when you come back, we can vote on it. So take a screenshot before you head over. I believe I'm going to visit group 2 for this question. Hello, everyone. Mark, Melania, and Nico and Rosali. What do you think about this question? How do we get velocity from a position graph? So remember this?
The velocity would be the derivative of the position graph.
Perfect, very, very good. Yes. So on the curve, how do we get derivative of a function on the graph? Is there a quick way to look at the derivative and say, yes, so it will be the slope. So all we need is to draw the slope for point ABC and see which one has a positive or negative slope, right? So we want to find a positive velocity. So we just need to figure out which one has a positive slope. So it looks like which point or points have the positive slope? C and B, very good, Nico. So it's C and B. And between these 2 points, which one has the negative acceleration, the one that we want? It's the C, right? So how do you know it's C? I mean, how do you tell from the graph? That point you have a negative acceleration.
So the acceleration would be the second derivative of the position graph. So like the slope of the slope.
Okay, yes.
Be like how like the slope is changing like at that point, right?
I think, yes, I think I know what you're saying.
I think I'm thinking of it like in terms of calculus.
Yes, I do. One way is you can try to write out a sine function for this curve and take the second derivative. Or you can say how the slope is changing. I totally understand what you're saying. So let's see if that would help. So here you have a slope and later on your slope is becoming flat. So the slope is decreasing. Okay.
Yeah.
So so the slope is decreasing, meaning that, okay, whatever velocity is, your acceleration is in the opposite direction of your velocity, right? So here my velocity is positive, but the speeding up, the rate of change is getting smaller. So my acceleration is opposite, is negative. Is that how you would think about this?
Yeah, I think so.
Yeah, very good. That's a very good approach. But when you do this approach, be very careful. Here, my slope is positive. But if you're looking at a section with a graph that is below the 0 point, then you gotta be very careful thinking, okay, what does this mean, right? What does this represent?
Okay.
There's a faster way to do this is, okay, I know that the acceleration is always opposite to the position, right? Because this is my Hooke's law. Whatever your position is, your force is dragging it back. So whenever your position is positive, your acceleration is negative, because the spring is always trying to pull you back to the original position, to the equilibrium point. You can see that. So C, my positive position gives me a negative acceleration. All right, very good. Excellent job, everyone. I will see you when we get back.
Thank you.
All right, so looks like we have the majority of the vote. Let me go ahead and end this. We'll take a look at it together. Okay, so we are kind of the difference choices between A and C. They do have one thing in common, is that the position of these 2 points are above the 0 axis. Okay, that's very good. So we know that if the position is positive, then the acceleration must be positive or negative. So Hooke's law is telling us that your force is always in the opposite direction of your position, right? So if your position is positive, then the force to try to pull it back, then the force must be pointing in the negative direction. Very good. Thank you. Okay, so that means A and C both have the negative acceleration that we wanted. Okay, but between these 2 points, which one has a positive velocity? So from a position graph, how do we get? Sorry.
C does. It has the positive velocity because you just have to look at the slope, the tangent line at that point.
Excellent. So this one has a positive slope where this one has a negative. Excellent. So the answer would be C. I want to mention in my group, we had a good discussion. Melina mentioned that you can look at how the slope is changing to figure out the acceleration. So in this case, the slope represents velocity. So velocity here is this much value, and a later point, you can see velocity is 0. So the velocity is slowing down. That shows the acceleration is in the opposite direction of your velocity. So if your velocity here is positive, then the acceleration there is negative. So that's also a very good method to figure this stuff out. All right, let's continue to look at another question. Here we have a mass that's hanging from a vertical spring that is lifted at distance d above the equilibrium and is released at t equals 0. So some of you guys have done lab 12, right? I know not everyone does. Some of you have. We have looked at simple harmonic oscillation in the lab. That is exactly a spring going up and down with a mass attached to it. So they give us the initial condition. Initial condition is being that t equals 0, you are at a maximum distance d. Okay. So which one of these describe the correct function for velocity and acceleration graphs? Okay. We know that, okay, what we can have two different methods. One is let's simply write out our position function and take derivatives. We can do that. Okay, so how do we write our position functions? Right now, we just gonna rely on we're not going to solve the differential equations all over again. We're just saying, okay, we're looking at a sinusoidal function and we are going to make it in such a way that it match up with the initial conditions I was given. So at t equals 0, your position has to be at distance d, okay? So how do I write this position function so that it worked out? First of all, do I need a cosine or do you want to use a sine function?
For position?
Yes, for position.
Probably a cosine function, just because, well, that's the one we usually used. And no, never mind, just because it's the one we usually use.
Okay, totally. Knowing that you can always have a choice between sine and cosine, because the only difference between cosine and sine is a phase difference of pi over 2. So either way, but the most simple one here would be use a cosine, because at t equals 0, cosine give us 1. Cosine 0 give us 1. So that's a maximum value. That's what we want. And it's at distance d, so I multiply d. So that's it. That is my position function. So at t equals 0, it is at d. That's what's given to us. So I'm going to take the derivative and give us the velocity and acceleration. You can see that you take derivative with respect to time, you would get a negative omega sine omega t, right? So take a look at this. You need a negative sign, you have a maximum velocity and the sine function. So only this one match up. And the acceleration, you would have to take derivative one more time. You again have, so it's negative cos omega squared d cosine omega t. So it match up with this one. So A is the correct choice. That's first method. The second method would be, okay, simply let's evaluate which one give us the correct initial position. So this one tell us at t equals 0, you put it at a distance and you let go. So at t equals 0, your velocity should be what value? Positive, negative, 0? At that moment, I let go and let it oscillate. At that moment, what is my velocity?
Should be 0, right?
Yeah, because it hasn't moved anywhere yet. So not looking at after that moment, looking just that one instant. So that instant, it still has 0 velocity because it hasn't dropped yet. It just I just let it go. Okay, so you see that it cannot be cosine function because at t equals 0, I need that sine function to give me 0. Sine of 0 is 0. Good. So I know either this one or this one. And then I look at, okay, this one tells me right after t equals 0, it's going to give me a negative velocity. So let's see. Okay, so after you let it go, which way is it going to go? Is it going downward or upward after you drop? It's going up or down?
At first, it's going down, right?
Yeah, so because the spring is now being lifted up. So once I let go, it would go down. And the downward direction is opposite to what I have defined to be positive. So it would reflect on the mathematical equations to have a negative velocity right after t equals 0, negative. But later on, as time goes on, you would have positive velocity. Once it goes to the lowest point, it will come back up. And the sign will take care of that. The sign of something at a later time when t gets bigger, sign will become a negative value. So negative, negative will give us the positive velocity that we wanted. But right after t equals 0, you should have a negative velocity. So looking at initial conditions, you can also figure out the choice is A. Okay, so two different methods. Both of them works. Right. Wait a minute. Okay, so this is one we just did. We did this method already. All right, so going back to a bridge question by looking at two simple harmonic oscillators going back and forth. There are two cases. You can see what they have in common is they have the same spring and the mass. What is different between them is one of them is let go at -1 units. So they oscillate back and forth between -1 and 1. The other one oscillate with a double the amplitude, right? Much, much further in, much, much further out. So between these two cases, how do the maximum velocity compare? Do you think that maximum velocities between them are also doubles, or maybe 4 times, or maybe one of them is half of the other? So do you think this one you should have already done this question, right? I'm going to give you a hint by going up a slide, showing that how does our velocity look like? Our velocity looks like this kind of function, right? We said the correct choice is A. Now A shows my maximum velocity is omega times d. Okay, maximum velocity for a simple harmonic oscillation is omega times d. So in this case, case 1, V max is omega d 1. Yes, go ahead.
All right, since it's double now, it should probably be twice as big.
Yeah, we doubled the distance d, the amplitude, so the velocity also doubles in case 2. Because you can see our maximum velocity is omega times the amplitude d. So if d doubles, velocity doubles. So the B is correct. You can also answer this question using the energy perspective. You probably were wondering, thinking, okay, wouldn't the, if I double my amplitude, what I'm giving the oscillator 4 times of much of the energy? Yes, you did. So in case 2, you gave the mass m 4 times the energy as case 1, because the elastic potential energy is 1/2 kx squared, right? So potential energy from the spring is 1/2 k delta x squared. So for case 2, your potential energy is 1/2 K2 d squared, whereas in your case 1, your potential energy is only 1/2 K d squared. This is 4 times of the energy of the other. But if we use a energy approach, we can see, well, this is really just a transformation between potential energy to kinetic energy. So when all of the potential transform to kinetic, that's when my mass has the maximum velocity, right? When all of the potential, when it's fully stretched, is all potential, 0 kinetic. When it's in the middle is 0 potential and all kinetic. The 0 potential because the spring is not stretched in the middle. So at that middle point, your velocity is at a maximum. So you can see velocity is also squared. So even though this is 4 times of the potential here, because velocity is squared, makes my maximum velocity only doubles my maximum velocity in case 1. Okay, so the answer would be B. Again, 2 different approaches to answer this question. Whichever approach you use would give you the same result, the same thing. Okay, so that's one, that energy considerations. Conservation of energy approach is still, of course, valid for simple harmonic oscillation kind of problems, also very useful because for a question like this, when you're asking to solve for speed, you can ignore whatever complicated process in between. You can simply pick your initial point and your final point, and then the result will be very quick. You can solve the results very quick. You do not have to go to writing the actual equations for velocity. Sometimes that could take a little bit of time because getting the sines or the cosines to work out and getting the phase correct, that still takes some time. But if you use the energy approach, it would be very quick, right? The energy at either this point or this point is all potential. That's 1/2 K times amplitude squared. The energy in the middle is all kinetic. That is 1/2 mv squared. V is a maximum value there. So you can solve for velocity maximum as a function of your amplitude. And your omega is square root of K over M. Let's not forget that. That is an intrinsic nature of your spring. So if you're given a spring K and you're giving a mass M, then omega is already fixed. And you can see it doesn't really, matter whether you're letting it stretch out further and letting it go or letting it stretch out a little bit and let it go. It will all have the same omega because omega is square root of K over M. Now, energy approach can also help you solve anywhere in between these 2 points, right? If you're halfway in between 0 and A, let's say this is at A over 2. Now I'm asking you, what is your velocity? Would you be able to solve that? What is your velocity at that point? So you can see using an energy approach, this should also be easy to do because you will say, okay, my initial point is still, let's choose potential energy at a maximum value is 1/2 Ka squared. It's all the way stretched. Now my final point is halfway in between. I have some potential energy. It's not as big because I'm halfway in between. I still also have some kind of kinetic because I'm also moving, right? So I still can use an energy approach using E final is equal to E initial, no energy transfers. So 1/2 mv squared plus my potential energy is equal to all the potential energy I had in the middle. So I can still solve for velocity at that point. So this is still valid, okay? So whichever point I give you, as long as you know how much it's stretched at that point, you can solve for the velocity at that point, and vice versa. If I tell you what is the velocity at that point, you can solve for exactly what location you are at, how much your spring is being stretched or compressed. So you can see that is all done using the conservation of energy approach. You can, of course, figure that out using the equations for velocity as a function of time. But to do that, you need to first calculate the position function and then take the derivative, get the velocity function. And then you can figure out your velocity at any given moment. So for example, if I wanted to use that approach, I would say, okay, if my position is now a over 2, okay, so that is a cosine omega t. So I need to figure out what is my t. And then I plugged in into the velocity graph, which is negative omega a sine omega t, and then plug it in this t to figure out your velocity. It still works. So we will get more into that detail later in the class. Okay, so that's all we have time for today. On Wednesday, we will continue to look at simple harmonic oscillation and look at more problems, okay?
Professor, could you scroll up a little bit, please, to that? Yeah, right there. Thank you.
Sure. All right, I'll see you all on Wednesday, and have a good rest of your day. Bye, everyone.
Bye, Professor. Thank you. Have a good weekend and Thanksgiving.
Thank you, and you guys too.
Well, we'll see you on Wednesday, but yeah.
Right.
Bye, Professor. Thank you.
Goodbye.